So now we're going to take a look at rational functions. A rational function is a function that can be expressed as p of x over q of x, where p of x and q of x are polynomial functions, and q of x cannot equal 0. So some examples of rational functions are x squared over x minus 2 and 1 over x squared. X minus 1 over the root of x plus 2 is not a rational function because the denominator is not a polynomial. So in this investigation, we're going to take a look at 3 types of rational functions. So please pause the video, and then once you've tried the questions, come back and check your work. So part A, our rational functions of the form a over bx plus c, where a, b, and c are real numbers. So where are the zeros? We can see for a polynomial of this form, there are no zeros. This function does not cross the x-axis. And you can prove this by solving the equation for 0. So we let f of x equal 0, and we see that 0 equals 1 over x minus 3. Multiplying both sides by x minus 3 gives us that 0 is equal to 1, which we know is not true, so therefore this function does not have any zeros or does not touch the x-axis. If we want to determine the y-intercept, we let x equal 0. Therefore, f at 0 is equal to 1 over 0 minus 3, which is equal to negative 1/3, which we can see here on the graph. So we have the point 0 and negative 1/3. F of x is a function since it passes the vertical line test, which means that for every x value, there is only one y value. So for our domain, we see that x is any real number. However, x cannot equal 3. And for our range, y is any real number, and we see that y cannot equal 0. F of x is a discontinuous function, and is discontinuous at x equals 3. We note there's a vertical asymptote at x equals 3. And if we look finally at the end behaviors, as x goes to infinity and as x goes to negative infinity, so plus or minus infinity, we see that y goes to 0, which tells us we have a horizontal asymptote at y equals 0. Second example. Again, we're going to show that there are no zeros. You can solve for the y-intercept and you'll end up with 0 and 1. F of x is a function since it passes the vertical line test. You can show that the domain is x is any real number, however x cannot equal negative 2, and the range is y is any real number and y cannot equal 0. This function is discontinuous at x equals negative 2. We can see from the graph there's a vertical asymptote at x equals negative 2. And if we look at the end behavior, as x goes to negative infinity or as x goes to positive infinity, we see that y goes to 0 again. So this tells us we have a horizontal asymptote at y equals 0. And the last one. So are there any zeros? Once again, we can prove there are no zeros. For this one, if you solve for the y-intercept, you should get 0 and positive 1/3. This is a function. The domain is that x cannot equal 1.5, and the range is that y cannot equal 0. This is discontinuous at x equals 1.5. There's a vertical asymptote at x equals 3 over 2. And how can you get that? Well, if you look at the denominator for this expression, we know that this function, 2x minus 3, if it equals 0, my function will be undefined. So if I solve this equation, I'll get x equals 3 over 2. And once again, if we describe the end behaviors, as x goes to plus or minus infinity, y goes to 0. We have a horizontal asymptote at y equals 0. So let's summarize functions of the form a over bx plus c. First off, the horizontal asymptote is always going to be at y equals 0. We can determine the vertical asymptote by letting bx plus c equals 0 and then solve for x. That'll also give us our domain. We notice there are no zeros for rational functions of this form, and the y-intercept can be found by letting x equal 0 and solve for y. Next are rational functions of the form ax plus b over cx plus d. This time we find we have a 0 at x equals 3. And we can solve this algebraically. We can say let f of x equals 0, so the y value equals 0. We get 0 equals x minus 3 over x plus 2. First of all, I'm going to multiply both sides by x plus 2 to get the x plus 2 out of the denominator. And I end up with 0 equals x minus 3. And if I solve for this equation, I get x equals 3. So there is my x-intercept, or my 0. To find the y-intercept, same as before, let x equals 0. We get f at 0. That's 0 minus 3 over 0 plus 2. And we see we have a y-intercept at negative 3 over 2. And again, we can show that on our graph right here. This is a function. The domain is that x is any real number, but x cannot equal, if we look at that line there, x cannot equal negative 2. And the range, y is any real number. However, in this case, y cannot equal positive 1. We see that the vertical asymptote is at x equals negative 2. And for our end behaviors this time, we notice something new. As x goes to plus or minus infinity, we see that y actually approaches another number, a number other than 0. We see it approaches 1. So for this example, we have a horizontal asymptote at y equals 1. All right, next one. I'm going to go through these a little bit quicker. So 0, you can solve and show that you have a 0 at negative 2. You can also solve and show you have a y-intercept at 2. So here's our 0. Here's our y-intercept. This is a function. The domain is that x cannot equal 2, and the range is that y cannot equal negative 2. This function is discontinuous at x equals 2. There is a vertical asymptote, and this time it's at x equals positive 2. If we look at the end behaviors, once again we see as x goes to plus or minus infinity, we see that y goes to negative 2. So this tells us we have a horizontal asymptote at y equals negative 2. And the final one. This time we have a x-intercept at negative 4 over 3. And we have a y-intercept at 0 and 2. This is a function. The domain is that x cannot equal negative 2, and the range is that y cannot equal 3. This function is discontinuous at x equals negative 2. There is a vertical asymptote at x equals negative 2. And we notice again for our end behaviors, as x goes to plus or minus infinity, this time it approaches another number. This time it approaches 3, which means we have a horizontal asymptote at y equals 3. So the final question on there is, without graphing, how can you predict where a horizontal asymptote will occur? Well, if you look closely at the leading coefficients of all these graphs, you should notice something. Let's start with the first one. The leading coefficient is 1 over 1. 1 divided by 1 is 1. And notice our horizontal asymptote is 1. Next one. We see that our leading coefficients are 2 and negative 1. 2 divided by negative 1 happens to be negative 2. And the final one, 3 over 1. 3 divided by 1 is 3. And notice that matches our horizontal asymptote. So for our first set of graphs, they were all 0. But if we put a linear function over a linear function, the horizontal asymptote will be anything other than 0. So let's summarize. So for a function of the form ax plus b over cx plus d, the horizontal asymptote is y equals a over c, the leading coefficient of the numerator divided by the leading coefficient of the denominator. The vertical asymptote is still determined by letting cx plus d equal 0 and then solving for x. The zeros can be determined by setting f of x equal to 0 and then solve for x. And the y-intercept can be determined by letting x equal 0 and solve for y. All right, final set of rational functions. This time a quadratic over a linear function. So, where are the zeros? We see for the first one, there are no zeros. And we can prove this algebraically. So we can let f of x equal 0. So we get 0 equals 0.5x squared plus 1. So now let's try to solve for x. We get negative 1 equals 0.5x squared. Then we get negative 2 is equal to x squared. So x is equal to plus or minus the square root of negative 2, which if you use your calculator, you'll see you'll get an error. So there are no x-intercepts for this function. Let's look at the y-intercept. Remember, we let x equal 0. So we have f as 0 equals 0.5 times 0 squared plus 1. So we get 1 over 0 plus 2, which is 2. And we have a y-intercept of 0.5, which we can see right here. This is a function. We can see that the domain for this function is that x can be any real number, but x cannot equal negative 2. The range is much trickier. We have y can be any real number, but we have these two sets of restrictions. Y has to be bigger than all these values here, and y has to be less than all these values here. So we got the space in the middle that it cannot equal. So you'd need some graphing technology to figure out the local max and local min of this function, which would be somewhere here, let's say, and maybe somewhere here. Maybe that's even the local min. So we're not going to worry about the range for this type of function at the moment. This function is discontinuous at x equals negative 2. That is where there's a break in the graph. There is a vertical asymptote at x equals negative 2. And notice there is no horizontal asymptote. We have what's called a slant asymptote. And it is actually an equation of a line, y equals 1/2 x minus 1. If you were to look at the end behaviors for this graph, so as x goes to infinity, we see that y also goes to infinity. And as x goes to negative infinity, y goes to negative infinity. So notice this graph is going up to the right as we go to infinity. And then as we look at the negative, it's going down to the left. But what happens is this curve, f of x, approaches the line y equals 1/2 x minus 1. If you were to graph this in Desmos and zoom out, all you would see is a straight line if you zoomed out far enough. And it would have the equation 1/2 x minus 1. How do you get that equation? Well, if you look at part H, I asked if you would take your function 0.5 x squared plus 0x plus 1 and divided by x plus 2. And if you do that, you're actually going to end up with 0.5 x minus 1, which happens to be our oblique asymptote or our slant asymptote. Second one, following the same steps. You tried to solve, you would get the zeros negative 2 and 2. You would find out you have a y-intercept at 0 and negative 4. This is a function. This one we can find the domain and range for. We see that x is any real number, but x cannot equal negative 1. And notice the range this time. This is the first time we've seen this for a rational function, that y can be any real number. This function is discontinuous at x equals -1. There is a vertical asymptote at x equals -1. And if we describe the end behaviors again, we see that as x goes to infinity, y goes to infinity. And as x goes to -infinity, y goes to -infinity. So while this doesn't have a horizontal asymptote, we see that it starts to follow the trend of this dotted line, y equals x minus 1, or what we call an oblique asymptote. And if you wanted to find that equation, you would take your x squared minus 4, and you would divide it by x plus 1. And you see you would end up with x minus 1. So there is x minus 1. There is our oblique asymptote. They are the same equation.